Let's start the stone rosette, which we have started already in the last class. Now, like stresses, strains can also be shown graphically and calculate graphically. You know, in our study of strength of material in third semester, we have the analytical calculations of the stress, normal stress and shear stress acting over an oblique plane while of a prismatic bar which is subjected to stresses or load, tensile loads or compressive load along x-axis, along y-axis, as well as shear stresses along xy axis and y-axis, etc. And we have calculated the value of sigma n, normal stress, and calculated the value of tau n, not shear stress acting on a oblique plane, which is at an angle theta over x-axis itself. This process, the calculation of sigma x and sigma n, sigma x and tau n, and that is the maximum value of it. What is the maximum value of it, and what is the maximum? What is the value of the angle? I mean the angle theta over what is the plane over which both these values are maximum? We have calculated analytically. Next, what we have done, we have followed a strain. A Morse circle is a theory known as Morse circle. You can calculate all this stress analytically, and you can calculate all these stresses by charging the length of the respective stresses as per a known scale selected by you yourself, and you can from the circle thus produced by a particular specific process, we can calculate from the circle itself different specified length from the circle itself the value of the sigma n or maximum stress acting on which angle, and value of tau n we acting on the oblique angle, and what is the angular obliquity, and what is the maximum value of sigma n, and what is the maximum value of tau n, and over which angle or which plane it is acting. So same now we are working over. We have done the Morse circle application of Morse circle in our stress analysis. Now we want to do the application of Morse circle on our strain analysis. In SOM also, SOM or strength of material subject also, we can calculate the two-dimensional strain acting over two axes, xy and ox and oy, by using the Morse circle itself. Now here strain angle we can see graphically, and Morse circle of strain is more or less similar to Morse circle of stresses itself. Here, instead of knowing the direct shear strains only two mutually perpendicular strain, we obtain three or more direct strain in any three or more node direction and on an exposed surface, say on an exposed plate itself, on exposed surface of the concerned material whose stress or strain you want to know. This procedure is more often used by employing electrical resistance strain gauges, and a group of these strain gauges fitted at a point in a specified direction known as strain gauges itself. So what you have to do, you want to know the strains, you want to know the stresses, but how can you calculate stresses? You have to do in three different ways. You have to calculate the strains, and you have to convert by using the Young's modulus the corresponding stresses. If you can first calculate, then you can measure the stresses, measure the strains, means the deflection or deflection per unit length along a certain direction, and use them to know the value of stresses, to calculate the value of stresses on that particular direction itself. That is the use of doing the strain gauges or strain rosette and strain rosette system. What is strain rosette? Actually, what we do in our practice, we are supposed to know the stress along a oblique plane and stress normal to the oblique plane itself, and what is the orientation of the oblique plane along x-axis, etc. But we do not set the strain gauges normal or shear on or along and any other stress itself on any plane itself. We set it on the concerned subject, concern you see the member with whose stress you want to know on a visible surface, not inside the surface itself, inside it, but on the visible or viewable surface by a group of gauges. We've set these gauges as a group and say minimum 3, maximum can be 6, etc. And it's this group of stresses is defined as the strain rosette. Means this group of strain will give you the strains on a specific direction, and from the strains you can calculate the stresses if necessary. Now, what are the type of strain gauges? What are the type of strain gauges? Just one second, view. What are the type of strain gauges? Theoretically, the angle between the strain gauges in a strain rosette could be anything less than 360 degree and could be anything more than 0 degree. Means if you go through a line, draw a straight line, say along x-axis, and any angle measured in the clock or plotted in the clockwise direction more than 0 and less than 360 means total rotation, we can put and calculate on strain axis itself. So unexpected start. So we have to expose it to on an exposed surface. We can set this type of strains accordingly. But for the phase of calculating and drawing, it is customary to use a certain common angle. You can do on any angle, but it is the practice to do a certain common angle, like say 60 degrees, like say 45 degrees, like say 30 degrees, like this. Incidentally, this avoids the yield condition of the equation as well, avoid the two additional complications of the equations as well. The most common strain gauges are three strain gauges. Three strain gauges say rectangular type, delta type, 4 element sources, rectangular. No, sorry, 3 element strain sources. One is rectangular type and one is delta type, and 4 element stresses. That's also same. One is rectangular type, another is T delta type. What are these? Say here we have 3 element stresses. That is, one is say 1A, the another is say B, another is say C. Now what happens here? You set this should be an angle O, set from O to A, the strain gauge is A, which is actually along the x-axis. From here x to B, x, we have to do theta C, which is 90 degree, and you have to set another strain gauges there. That is strain gauge number 6, and from OX to BOB, that is 45 degree, we can set one strain gauge like this. This is the rectangular strain gauges, a set of 3 elements rectangular strain gauges, strain rosette. The delta type, how we can do the delta type strain rosette, and 3 elements strain rosette. Here is also 1, 2, and 3. Here is also 1, 2, and 3 gauges, not more than that. Again, say this point is 0, O2X is a strain. Strain rosette, strain gauge number A is set there, and from O to B, which is away by angle theta B, which is equal to 120 degree here. This is set, another strain gauge is set here, which is definitely as per our theory. We should drop it more than 1. We should drop. We should be more than 0 degree and less than 360 degree. It is more than 0 degree means it is 120 degree angle from OX. Next, thrust losses is set at an angle 240 degree, which is less than 360 but more than 0 degree. So it is total put here. So this is looks like a delta, and thus it called that delta rosette. Here look, it looks like the sides of the rectangle, so you can call rectangular rosette itself. Now, four element rectangular rosette itself, one is OA into X. There is four elements, 1, 2, A, B, C, D. A is generally put here at A axis, and along X axis is a theta B is put say around theta B is put, theta D is 130, theta B is around 45 degree itself, theta D is 135 itself, and theta C is 90 degree itself. So 1, 2, 3, 4, four rectangle, four separate elements rectangular rosette itself. T delta rosette, it's look like a delta, at the same time it looks like a T somewhere. How it is processed? Again, A is gauge name A is put along Y axis, gauge name B is put along OB axis, and gauge name C put along 240 degree অর্থাৎ axis, that is OC, and gauge along D is put along 90 degree from OA axis. So what we are doing here, that is 140 along from here, 120 from here, and 90 from here. These are the T delta. Theta B is 90, theta C is 240, and theta this angle theta D, you can say it is equal to 90 degrees, sir. These are the four different type of strain rosette generally we can use and do our calculation itself. Now, here this strain rosette can be analyzed by means of the figure as well as by means of the equation epsilon r or ER is equal to EX square, EX into cos square theta plus EY into sin square theta plus gamma XY sin theta cos theta, which is the eccentricity, I mean the elongation, or not elongation exactly, the strain along a particular line, say PQ, which started from P to Q and with a certain initial length. When it is a the straight line P to Q is a part of the it is situated, or it's a part of a solid mass, which after the additional of some external gauges, which after the addition of some external gauges will take the form, say PQ dash, and due to this I mean the movement or shifting of the from original position, this is also liable to have certain eccentricity itself, silent elongation itself. That elongation is given as ER epsilon x cos square theta, EY epsilon into sin square theta gamma XY sin theta cos theta, where EX is the strain along X axis, strain along Y axis, and theta is the angle in between between the two line of action of the two stresses before and after the elongation itself, and gamma X the strain along XY axis itself. Now we can say from here this strain can be written as like this: if Ex cos square theta Ey sin square theta plus du by dy cos theta sin theta, du by dx cos theta sin theta also, and gamma theta p epsilon x minus epsilon y sin 2 theta plus epsilon xy cos 2 theta. And by calculating the epsilon and gamma from here, we can say the principal strain along one or principal strain will be epsilon 1, 2 Principal is epsilon 1 2 is equal to epsilon x plus epsilon y by 2 and epsilon x minus epsilon y by y plus gamma xy. And tan theta means line of action of this principal stress is gamma xy divided by epsilon x plus epsilon y. It was proved in your strength of material classes. And maximum stress will be ex plus ey by 2 plus half of this portion, and ex my minimum stress will be, or epsilon 2 will be ex plus ey minus 2 by 2 minus half of this portion. So we have to calculate. First we have to know what is, how we can get gamma x, how we can get epsilon y, how we can get epsilon x to know the principal x itself. Now what is the process of knowing it? First this for example, say we consider 3-element rectangular rosette. Then if the equation epsilon r, all these things just have shown here, just have told you here, what will be the epsilon a? Epsilon a, say here, this is the strain measured along OX axis, or epsilon x, or you can say that epsilon a, eccentricity I mean strain along A axis, can turn as epsilon a, and can also be turned as epsilon x axis, because we are plotting x axis along this direction, horizontal axis along this direction itself. So epsilon a is the epsilon x axis, means the strain gets set here and measures the value of the strain along a direction is given by our epsilon x axis. And epsilon b, what is epsilon b? Say this is the epsilon b. The in between angle is 45 degree itself. Okay, and if we plot and epsilon y is plotted along c axis, because this is the vertical axis itself. This is along y axis, or this is plotted x axis. So we know the value of the strain along OX axis, and we know the value of the strain along OB axis, or this can be said as epsilon a, this can be said as epsilon b, this strain can be said as epsilon c itself. So if we put this value of strain in this equation here as epsilon r is equal to epsilon b, means this is the strain along an axis. We are considering that this was the position of our straight line is along x axis initially, and after deformation it took this position along OB axis, OB line, or it is situated at an angle equal to theta itself. Now so we can put the value of strain here, and at epsilon b, value of strain here at epsilon a, value of strain here as epsilon c, and gamma xy remains as it was itself. And then from this equation we'll have, I'm wrong. If we put the value of epsilon b here, which is 45 degree with x axis, epsilon x here, which is along x axis, and epsilon y here, which is along y axis, and also we can use this equation because you have to put the value of u and y here, and you can come here, or come this equation, epsilon x in epsilon r is equal to epsilon x cos square theta plus epsilon y is epsilon y sin square theta plus gamma xy sin theta cos theta, where we have put epsilon b at epsilon r, which is known to us, and epsilon x is equal to epsilon a, epsilon y is equal to epsilon c, and cos theta is equal to 45 degree. So cos square theta will become half, sin square theta will become half, and multiplication of sin theta cos theta, or sin 45 degree plus sin cos 45 degree, which is equal to 1 by root 2 multiplied by 1 by 2, again becomes half. So half should be common here, like here, half epsilon x6 or epsilon a plus epsilon yy or epsilon b plus gamma xy or gamma c of gamma xy. And this is epsa C, epsa A, and epsa B, and gamma xy remains unknown. We have to calculate it from this equation, and epsa C is epsa yy here. So gamma xy you can calculate 2 into epsa B minus epsa A minus epsa C. So we can use this above equation like here. Just 1 second, please. Okay. Now let us go to the next pages. Now with the value of epsa A and epsa C, this is the measured strain along A axis, along the X axis on A, plus epsa C is equal to epsa Y, or is equal to measured strain by strain rosette along Y axis. Put this value of gamma A, epsa and epsa Y, and put the value of gamma XY here, and all of them we can calculate, because all the values are known. So we got the principal stresses here. At the same time, with this equation, while gamma x you have calculated, epsa x and epsa y are known to you, you can now calculate the value of theta, which is the in between angle from the x axis, so is that of a plane where the principal stresses are acting over it. Now, similarly, other case can be created. In the cases of an element, say y, just 1 second, it is the element of y element rosette. No, four element rosette. We can have 3 element rosette, and sometimes you see in the earlier example that can we have 4 element rosette. But what exactly we are supposed to do with the additional element, because we need the 3 strains only. We have 1 extra strain gauges here as the fourth gauges, which is strictly not necessary, but we can use for checking purposes as one of the strain gauges is effective or not in a 3 element rosette. The fourth gauges is used to know the position or actually the situation of the 3 element gauges itself. Now, there is no way to check the reading and get the correct result unless you know correctly that stresses are wrong, or these gauges are wrong or right. So in the sense of same 4 element gauges, we can verify whether the gauges are correct or not. Say a 4 element rectangular straight gauges, we place the first gauges as at OX, that is equal to 0, second 45 degree, that is EB, third 90 degree, that is AC, fourth 135, that is ED, A, B, C, D gauges. So the configuration ensures a quick check. From the separation of the first material, you see J1 is as per our value equation of invariant. J1 is EXX plus EYY. Such EXX and EYY is equal to EA epsa A plus epsa C and plus epsa plus epsa D. Just we have seen in earlier part of this equation. This gives an informative check if this value of the right hand side matches with the value of the left hand side, then your gauges are okay. If not, then we have some problem with one of them. So you have to check them or replace them. Sorry. Well, let us go through another thing which is defined as Murphy's construction. We have just talked about Morse strain gauges, Morse cycle, Morse strain gauges. In case of three-dimensional stresses, we use this construction as Murphy's construction. Here we show, here is Morse cycle of strain, but it is defined as Murphy's constructions. What we do with the help of three direct strains we are using. We know we have for the rectangular gauges three direct strains along x, along 45 degree, along 90 degree. Suppose may not be these strain gauges A, B, C are oriented as in the figure itself. There's the angle in between angle is not 90 degrees. Say from the angle OX axis, this is epsilon A1. This is the principal line, principal gauge line, maximum strain line, and the rosette OA is inclined by an angle phi from epsilon 1 from O epsilon 1. Rosette B inclined by an angle alpha from A, and rosette C inclined by an angle beta from B itself. Now, and phi is the unknown angle of the gauge A with the principal strain direction. Unless we know the f psi x, f psi y, you cannot calculate, nor you can plot the principal strain itself. Now, to construct the straight cycle of stresses, first draw a vertical line here. What we are doing here, I'm just narrating it from my notes. Now to construct the cycle of stress, first draw a vertical line here. Okay, and a horizontal line here, that is along OX, and that is along OY as well as gamma XY along the axis, shear strain axis. Then measure first of all f psi A, f psi B, and f psi C. Measure the strain here at A, at B, and at C. Then plot this value of A, of B, and of C here over the OX line or say x-axis with the help of a suitable gauge itself. Then, so we have got 3 points. One point is here A, 2 points B, third point here C. So drop a vertical here. This, and this. 3 verticals are drawn. These verticals are parallel. Now, what we are doing, we first select one point P1 here over the line f psi B itself, any arbitrary point. It is your choice. Next, draw a line by an angle equal to alpha, which is known to you from the vertical to this angle. Draw a line at an angle alpha from the vertical, and it will go on and move on and touch the line of the vertical at A, that is P, that is called point 2 or P2. Again, you draw an angle beta, but not in the same direction but opposite direction beta, and draw a line which is at an angle beta from the vertical itself, which intersect here the vertical drawn from the center C at here. So we have got 3 points P1, P2, and P3. And the circle drawn through these 3 points P1, P2, P3 will be our required Morse cycle itself. And OX1 and OX2. What is OX1? The point of intersection of the circle. Point of intersection of the circle OX, intersection of the circle with the x-axis, that is x2, and that is the maximum or principal stress or major stress. And OX1, the point of intersection of this point here of the circle with x-axis itself, with the minor or lower value of the principal stress itself. Thus, it is a general construction, but particular axis of strain gauges is also very simple itself. Thus, we have got principal strain and how we are getting the angle phi from the line P2 to P3. the angle intended is equal to 2 into phi itself, and that is equal, thus you can measure the value of 2 phi and divide it into 2 to get the angle phi with the value of with the value of maximum plane for maximum simple stresses. Thus it is equal to OX1 is minimum, OX2 is the maximum, and phi is the angle itself. Thus, this Mohr cycle can be used to make certain mathematical calculations. Say, let us have a problem here. What is given in the problem? The problem is here. Thus, this is given, it is a figure shown below. The strains measured by three-dimensional electrical axis as shown below is the in the figure A itself. First, find out the principal strain by transformation equation, mean analytical. Then also find out the same graphically and compare the result itself. What is given here is not written. I forgot to write it. Epsa A. Epsa A is given as equal to 700 into 10 to the power minus 6, or you can say micro Newton, or you can say, just 1 second, is a, yes, microcentimeter. You can say microcentimeter per centimeter. This can be also with drawing, or it can be it can be as 700 to the power minus 6 per centimeter elongation, because these strains are extremely small, not viewable at all. They can be measured in microcentimeter only. So epsa A becomes 700 microcentimeter per meter per centimeter, and epsa B is given as 300 microcentimeter per centimeter, or epsa C is same, equal to, that is again 300 centimeter per centimeter microcentimeter per centimeter of elongation, or you can say 700 epsa is 700 to the power minus 6 per centimeter, epsa B and epsa C 300 to the power minus 6 per centimeter per meter per centimeter. Next, how we can do the analytical calculation? First, we have to find out, we have to plot what is epsa X and what is epsa Y itself. Epsa X equal to epsa is epsa A, which I've just told you. Epsa X is along x-axis. It is given as central 700 to the power 6. Epsa Y is equal to epsa C, is equal to 300 to the power minus 6, and epsa X dash, which is supposed to be the change in length of strain of the line, original line, say PQ, which is changed to the length and orientation equal to a change in new orientation and a new length equal to PQ dash. So it is along the axis epsa B. So epsa B will be equal to 300 into 10 to the power minus C. Epsa A will be 700 into 10 to the power minus 6, and epsa C or epsa Y, I'm sorry, again I'm telling you, epsa C will be equal to epsa X dash equal to 300 to the power minus 6, epsa X equal to epsa A, which is equal to 700 to the power minus 6, and epsa C is equal to epsa Y is equal to 300 to the power minus 6 itself. Now, say, then we put the value of epsa X dash, which is 300 to the power minus 6, we put it here. We put the value of epsa X as 700 to the power minus 6, we put the value of theta as 45 degree, which is given in the standard set, and lastly we put the value of epsa Y or epsa C, which is again 300 to the power minus 6 multiplied by the cos 45 degree multiplied by cos sin 45 degree multiplied by cos 45 degree here, and this is sin square half multiplied by cos square half itself. Here cos theta is equal to cos 45 degree, so 1 by square root of 2 whole square. Sin theta is equal to sin 45 degree. Sin square theta is equal to sin 45 degree, which is equal to 1 by square root of 2 into whole square is also half. So all are equal to half, this is multiplied by half, this is multiplied by half, and this is multiplied by half itself. So gamma xy will become 300 minus 700 multiplied, that is 200 into 2 is 21 minus 6 itself. So thus we can calculate epsilon 1 by epsilon 2, because we know what is epsilon x, what is epsilon y, and what is gamma xy. We put all of the respective values and put 10 to the power minus 6 out of it, and put all their values in square, and after solving it will become 500 plus minus 200 into square root of 2 into 10 to the power minus 6, and epsilon max epsilon 1 by epsilon 2, which is become epsilon 1 and epsilon 2. Epsilon will be this portion plus this portion, epsilon 1 will be this portion minus this portion. Here minus is not clearly came off. Minus was there, but clearly was not reacted like this. So this is the epsilon 1 and epsilon 2. Direction of principal axis can also be found if phi is the angle of maximum principal strain with epsilon a. Is we have calculated gamma xy, we have calculated ex and uy, we put them together equal to minus 1, 2 phi equal minus 45 degree, and 135 degree, or phi equal to half minus 22.5 and or plus 67.5 degree. So analytically, thus we are calculating this strain. Let us calculate the graphical strain. How will you do the graphical strain? I'm going back to the same position here. Here we draw the line OY dash, this one, as the y-axis, and the OX dash, this one, as the x-axis itself. Then we drop parallel and BC and DC. We know the value of strain along at the point C, at the point D, B and C are same. So we have got only one line, straight line here, which is applicable for both B and C itself, and another line is the A here, which is as per the value of the strain calculated at A. So what we do here, the reading of strain gauge C is superposed as B, and thus we both points A and B on line AC. Now take a point on D on the line. Take a point D on the line, line B and C, and it is to be drawn by an angle 45 degree itself. Another line which is tangent at the point, at this point will be drawn 45 degree, just to show that the third, it is not interested in the circle anywhere, but it will show you the position of the third on the motorcycle itself, third gauge on the motorcycle itself. And this 45 degree line drawn by 45 degree with the vertical will go and intersect the x-axis at O and intersects at a-axis at A itself. Thus, if we draw a motorcycle to a circle with the radius OA or OB, we'll got a circle like this, where the maximum stress will given us from the cycle equal to O dash into 2, O dash into F, and minimum is the O dash into A, and the angle phi is given by OA dash itself. There are only 2 points B and C is taken by BA and the damage. Okay.